Bonjour tout le monde. My name is Subhashish Ghoshal, and I'm the director of the Trottier Institute for Sustainability in Engineering and Design, or in short, TISED. It's my pleasure to welcome you all today to today's seminar, Circular Economy and the Built Environment from Housing to Data. This is the first talk at our TISEDTALKS seminar this academic year, and very pleased to have you here. Before we begin, on behalf of TISED, I'd like to acknowledge that McGill University is located on land which has long served as a site of meeting and exchange among indigenous peoples, including the Haudenosaunee and Anishinaabe nations. We acknowledge and thank the diverse indigenous peoples whose presence make this territory on which peoples of the world now gather possible. And while we look forward to the day when we can host these seminars in person, I hope this is coming really soon. We'll just, for the interim time, just continue to meet in a virtual setting, just to navigate through the pandemic that's still with us as part of our daily lives. So a quick housekeeping note. We will, before we get started with the presentation, I just wanted to point out that we have some time where you can ask questions. And so please feel free to enter your questions during the presentation. We'll sort of collect them and then go through a question and answer session at the end of the presentation. So you can, if you wish to, also unmute your mic and ask the question directly, but the written questions, we'll go through them first. So with that, I'd like to introduce our speaker for today. We're pleased to welcome Professor Naomi Keena, who is an architect and an assistant professor at the Peter Fu School of Architecture. Professor Keena joined McGill in January 2020 and is actually one of our newest TISED members. Dr. Keena's research focuses on broadening the space and time upon which we consider architectural and urban design to understand both the work of the technosphere in constructing our urban environments and that of the geobiosphere in sustaining such development. She combines life cycle approaches to design with data visualization and computational techniques, and as a means to assess socio-ecological factors in architecture and to transform complex data streams into organized knowledge. Prior to joining McGill, Professor Keena was a scientific researcher and postdoctoral associate at the Yale Center for Ecosystems in Architecture, and a lecturer at the Yale School of Architecture. Professor Keena holds a PhD in Architecture Sciences from the Center for Architecture Science and Ecology, or CASE, at the Rensselaer Polytechnic Institute. Prior to her PhD studies, she worked in professional practice with internationally renowned firms in both the US and Europe. So with that, I'd like to turn the floor over to Professor Keena.
Thank you so much, Professor Ghoshal, and I'm going to share my screen. So I'm hoping that you're seeing my screen. Is all good?
Yes.
Okay, great, thank you. So many thanks to TISED. I'm very excited. It's a pleasure to be here today to talk about circular economy and the built environment. And as Professor Ghoshal said, I'm an assistant professor here at McGill School of Architecture. And prior to joining McGill in January this year, I was conducting postdoctoral training with Professor Anna Dyson at the Yale Center for Ecosystems and Architecture. So the work I'll present today includes collaborative research conducted at GLC, as well as some of the research I've started in this area during my time here at McGill. Okay, so a brief outline of what we'll look at today, and we'll start by explaining the contextual motivations of this research and look at some case studies. The first one is a data to knowledge framework that really looks at mapping the built environment process. We'll also look at a built project, which is a demonstration project called the Ecological Living module, which was looking at testing this built environment ecosystem framework and looks at a kind of regenerative design process. And the last one is looking at circular economy and how it can help the housing supply challenge within the context of Canada. So according to federal scientists in the US Fourth National Climate Assessment Report, understanding the consequences of climate change involves studying the interconnections between the natural, the built, and the social systems that we rely on and their vulnerability to cascading impacts. And it is these interconnections between the technosphere and the geobiosphere that the Fourth National Climate Assessment is really addressing. So if we think of the technosphere as our health and management systems, our socio-culture and economic systems, and the built environment process houses the technosphere. And it uses ecosystem goods and services, such as water, raw materials, energy, dissipation of waste, throughout the lifespan of a building. And stress on ecosystem goods and services can result in environmental overloading, which then has an impact and places stress on the geobiosphere, which has this adverse effect to the technosphere. So we can see that there's this very strong interrelationship between human activity and our reliance on the geobiosphere, or so-called natural cycles. And the latest IPCC report from June of this year highlighted this interrelationship. This was one of the first IPCC reports where they unequivocally stated that climate change is caused by human influence and activities. And this figure illustrates the history of global temperature change and causes of recent warming. And the report outlines the pathways limiting global warming of 1.5 Celsius require rapid and far-reaching transitions in, among other factors, energy and urban infrastructure, which includes buildings. So this forecast makes considering the reduction of greenhouse gas emissions in the design of our built environment ever more pressing. And why are buildings an issue? Well, on a global scale, buildings use 40% of resources, 25% of water, 40% of energy, and they contribute to approximately 1/3 of global greenhouse gas emissions. So this is where considering a circular economy in the built environment can be very promising. Unlike a linear economy, which is more typical in the construction industry today, and results in high consumption of energy, water, raw materials, and also high pollution in terms of emissions and wastewater and construction and demolition waste. A circular economy strives to improve resource efficiency mainly by closing the resource loop and by stopping the wasteful use of resources. And as climate pressures increase and material scarcity is imminent, systems thinking and innovation in material recovery will be critical to really helping ensure that built environments can embrace this kind of circular approach. And this is something that we explored through a report on circular economy in the built environment. And this report was part of a series of regional reports prepared by the United Nations One Planet Network Sustainable Buildings and Construction Program. And it looked at the state of play for circular built environment from regions around the world. So there was other reports looking at Africa, Asia, Europe, Latin America, and the Caribbean, as well as Oceania. And we were asked to study this state of play of circularity in the built environment for North America with a particular focus on the US. And as we did this, it became evident that there are a number of key challenges towards transitioning to circular economy within America. The first challenge is an entrenched linear material throughput economy. Within the US, there's this long established process of material extraction, manufacturing, transportation, and construction, and that's been in place since the Industrial Revolution. So it's difficult to change this without clear incentives. And the second challenge involves growing material consumption and associated waste in terms of material extraction. Here we see 2012 construction material figures that look at that 73% of all US raw materials, excluding fuel and food, were construction materials. And one of the key principles of a circular economy is decoupling economic growth from non-renewable material consumption. And we see here that this is the 2008 economic recession. And it's very evident that in terms of raw material use, and this is the construction materials, this big chunk here, that there's a dip in material consumption, directly associated with this, this economic recession. And we can see this throughout history. And if we think about then the end of life of materials, when it comes to municipal waste, in 2017 figures in the US, 52% of municipal waste went to landfill, and 25 to 45% of all construction solid waste stream was construction and demolition waste. And construction and demolition waste is at the deconstruction and demolition phase, but we also see it at the actual construction phase. And another key challenge was a lack of innovation or change within the construction sector. According to a US Department of Energy report, the compartmentalization and the lack of communication between building professionals in each of sector results in suboptimal designs and less than optimal building operations, while contributing to environmental impacts. And a McKinsey report on the construction sector echoes this view, defining the sector's lack of productivity and predicting that faced with sustainability demands, the sector will need to reassess how it builds to reduce waste and abate carbon emissions. And we can see from this report that's mapping productivity to digitalization, that the construction sector has grown less in terms of digitalization than other industries. Even industries such as agriculture, forest, fishing, and hunting have digitalized more. And at one point to note here is where advanced manufacturing is placed. Because one of the interesting things is that circular implementation is evident in other industries, such as advanced manufacturing. And one of the reasons for this, particularly in the US, that we found was that federal legislation allowed for and supported circular economy implementation and circular manufacturing. In particular, the Revitalize American Manufacturing and Innovation Act, or the REMI Act, which came about during the Obama administration, was a legislative basis for innovation within US manufacturing. And it promoted circular manufacturing and implementation and really helped bridge a gap between academic research and established industry partners. And although it was focusing on manufacturing, such as the automotive industry, the Act has led to a network of expertise in transitioning to circular economy that could be leveraged for the built environment. And some of the examples that we see here, these are images from various centers across the US that allow for either controlled off-site construction and modular construction assemblies, as well as innovation in building systems and using advanced manufacturing and technology. So in terms of circular economy principles in buildings, this concept can lead to principles such as design for disassembly practices or material efficiency and reuse. So the report really outlines steps towards transitioning to a circular economy. And I won't go into all of this today, but just to say that one of the steps is really the design of multi-beneficial policies that take a whole building life cycle and a systems thinking approach. Because such policies could allow for multi-stakeholder engagement and cross-industry collaboration. And this is key because currently the built environment process, and that is everything from extraction to the end of life, is siloed. And such a cross-industry collaboration is essential in facilitating circular strategies, which could potentially lead to amendments in policy and building codes. And one of the key takeaways that we took from the research was that technology and big data have a role to play because they can help to create these cross-industry collaborative networks. So the first project I'll show is a data to knowledge framework that really aims to use data to allow for cross-industry collaboration and to facilitate circular economy in the built environment, so that we can move from a linear material throughput economy approach to a more feedback reinforcing design approach. So this data to knowledge framework that I'll talk about today is called SEVA, Socio-Ecological Visual Analytics, and it's a web-based tool I've co-founded with my colleagues from ELC, Professor Anna Dyson and Dr. Mohammed Ali Etman. And the research objectives to this work were twofold. The first was by tracking carbon, energy, and material flows, we aimed to surpass the concept of a building and abstraction fixed solely in the operational phase, but rather as a system which undergoes multiple journeys of carbon, energy, and material transformation in its initial construction and its future dismantle. And such a system includes many stakeholders who represent each phase of the built environment process. And when I say built environment process, I'm talking about an understanding of the expanded multi-scalar ecosystem in which the built environment operates. And it's a chain of events that shape material and energy flows. And it starts here with the work of the geobiosphere, which can occur over millennia to produce many raw materials, which is currently not included in many life cycle accounting methodologies. And by including this important information on ecosystem goods and services and biogeophysical processes that we consider in material extraction, transportation, and manufacturing, we can understand the cost to the geobiosphere at each stage in the built environment process. And this could be revolutionary to thoroughly understand the environmental impact of the built environment process, akin to carbon accounting today. So as I mentioned, by tracking carbon, energy, material flows throughout the built environment process, and not just in this stage, the operational phase, we can really start to understand the impact from the initial construction to the future dismantle, and think of it as a system, right? A whole building life cycle systems approach. So this is the expanded scope in both time and scale, which we aimed to virtually map. The second research objective involved exploring how we can harness big data in mapping interconnections within the built environment process. So here we see the classic relationship of decision-making within the building sector. And this is much easier when we have small teams. But this research is towards an ecosystem intelligence and towards distributed knowledge across life cycle phases. This is particularly relevant to overcome the challenge of large projects with numerous different teams and complex information flows. So we question, how can we provide inclusive environments that link data, design, and knowledge, such as parametric environments that can constantly be reconfigured according to new information. So through this research, we introduced this data to knowledge framework named SEVA, and opposed to frameworks that have come before that are limited and disconnected, leading to siloed outputs at each phase of the built environment process. SEVA is novel in that it explicitly sets out to provide a framework that visualizes and connects the resulting outputs from each life cycle phase, offering this ecosystem intelligence to the built environment process. And data to knowledge and the way we share data is much more developed today than it was 20 to 30 years ago. Today, data to knowledge frameworks offer unprecedented opportunities in decoding complexity. So through SEVA, we're generating a knowledge graph of the built environment process, and we use semantic web ontologies to generate this knowledge graph. And this allows us to virtually connect each phase and its associated stakeholder, thereby conceivably acting as an overview tool for the built environment process. So we'll look at an example of how this virtual mapping may work. So at the material phase, we can incorporate embodied energy and carbon of different materials. We can explain material extraction and manufacturing processes. And since transportation has a major impact on material life cycle values, understanding the distance from source to construction site is important information to combine. And at the design phase, Multiple analyses can be viewed, from life cycle of the building design to integrated 3D models and energy and climate analysis to the resulting visualization, such as here daylight analysis, as well as different design options and their life cycle impacts can be understood. And integrating multiple aspects of the design, from renders and drawings to walkthroughs to live climatic data, which can help contextualize the building with changing climate over time. So we're including historic climate data, but also looking at live climatic data to really be able to understand changes to the climate and how that's affecting the building. And then during the construction and management phase, really using the framework to act as an organizational tool. So showing how different teams, such as subcontractors, for example, as well as budget and resources and personnel and big data can, and how data is being used, can all be organized and seen through the tool. And then during the operational phase, this may involve mapping data from Internet of Things and sensors, such as air quality data, and understanding the internal environment, as well as energy aspects. If there's any on-site renewable energy, being able to understand the energy generation on site, but also being able to understand the energy consumption. And this can allow for new ways of managing buildings and can also allow for occupancy comfort through the use of such data and by allowing occupants to have access to this live data feed. And then at the end of life phase, this becomes very interesting and can potentially really enable a circular approach, in that you can use the data from the material design and construction phases, such as understanding material composition of a material. For instance, here we see a data fitness ticket or material passport explaining the concrete used in the building on the left. And this helps inform decisions about material reuse or remanufacturing, as well as information about the construction assembly, which can be then used to help inform design for disassembly procedures or practices. So for this work, we hope that it can enable a built environment process which operates more as an ecosystem. And in collecting data on building projects from mapped built environment process life cycles, we can conceivably imagine a database of projects that can be searched by location, building typology, perhaps key performance metric. And the research has significance in multi-stakeholder engagement and evidence-based decision-making, especially within work which strives to find, solutions to grand challenges such as environmental issues. And by unlocking the potential of big data, we aim to facilitate the ability to project future scenarios towards more sustainable and progressive solutions. So it offers potential value to circular economy methods, amendments to building and policy codes, and the creation of incentives for cross-industry collaboration. So the second project I want to talk about today is this project called the Ecological Living Module, which was a collaboration between ELC, UN Environment, UN Habitat, and Gray Organsky Architects. And this project speaks to the regenerative principle of circular economy, which involves designing a building that goes beyond doing less harm, but actually can help the environment through its design. So it uses regenerative design principles to consider the whole building ecosystem, and it aims to create a resilient building that integrates the needs of society with the integrity of nature. So the context around this project was this, that the UN 2018 Revision of World Urbanization Prospects reports that by 2050, 68% of the world population is expected to live in urban areas. And as rates of urbanization increase to unprecedented levels, the urgent need for sustainable housing and infrastructure has become a widespread global challenge with social, economic, and ecological implications. And we know with growing climate change comes increased risk of climate change migration and the displacement of communities. And displacement is not temporary. The average time a family member remains in emergency accommodation is not weeks or months, but years. Actually, 18 years can be commonplace. So disasters create new permanent conditions. So our responses must not only be fast to deploy, but designed for these long time spans also. So with this research project, we introduced this new framework called the Built Environment Ecosystem Framework, and we showcased the framework through the Ecological Living module, which was this demonstration project. And the B framework takes an integrated systems approach with an aim to having synergistic impact. So we demonstrate how multifunctional interlinking of building systems that harness local bioclimatic resources such as solar, wind, water, biomaterials can more viably address a broad spectrum of sustainable development challenges while increasing local stakeholder agency. And the research outlines the ELM case study, which is a demonstration project that uses the integrated approach of the B framework and characterizes each design intervention in terms of the UN Sustainable Development Goals, or the UN SDGs. And this is interesting because the housing sector directly impacts the majority of the UN SDGs. However, striving to achieve these goals in a compartmentalized or siloed manner has impeded the implementation or transformational solutions that increase the security and well-being of urban populations. So the design of the ELM built on prior research that you're seeing here, and a number of different demonstration projects that really investigated and developed novel systems for a range of factors, from indoor air quality to water capture to renewable energy and circular material life cycles, and to considering how we acquire data towards socio-ecological design, to prior testing of the brief framework to other demonstration projects. And these are just some examples of the different prior research that we built upon. And as a background, the house was demonstrated on the UN Plaza in New York as part of a UN high-level political forum in 2018. UN Environment invited our center, the Yale Center for Ecosystems and Architecture, to design a microhouse to highlight the central role of sustainable buildings and how they address the UN SDGs, and also to address the need for quick deployable housing and infrastructure in the face of climate change migration. So the toolkit, if you like, or the framework of was to allow for this sustainable on-site self-sufficiency. And it's important to point out that we weren't suggesting that this home would be replicated, that this, that there would be a mass production, let's say, of the demonstration project of around the world. It was about a framework, this B framework, that had these principles and these tools that could be applied to create a similar building that was climate specific and that was region specific. So the key principles were resilient and adaptable construction techniques, renewable, locally sourced materials, secure on-site solar energy, sustainable water capture, purification and recycling, indoor air quality remediation, waste management, integrated and micro farming. And it also intended to offer possibilities for the growth of microeconomies through the generation of surplus resources on site, whether that be water, food, or power, which could be traded, providing an income stream to its occupants. So the module is constructed from locally harvested renewable materials. And while cross-laminated timber, which was used here, is a plentiful resource in North America, where this was being shown and designed for. In other climates, other material strategies could be employed. And bio-based materials allow for a circular economy. They can offer low carbon alternative construction materials by using low amounts of energy and carbon in their initial production, and by storing and sequestering carbon during the life of the building. So the ELM was self-sufficient in terms of electricity needs with on-site electricity generation. And we had two types of solar collectors. We had the traditional silicon panels and this novel integrated concentrating solar facade, which you can see on the roof here, which generates solar energy while allowing diffuse daylighting to pass through. And this is by helioptics, and the design of it was designed for many years by members from the ELC team. The water management strategies included rainwater collection, grey water recycling, filtration, and water generation, where humidity is extracted from the air to be used as potable or drinking water. And this system is linked to indoor air supply so that excess humidity indoors can be reduced and made more useful. And this was showcased, as I said, in New York in the summer. So it was quite humid, and it produced a lot of potable water, which was really interesting. So in terms of, this is the loft space, there's an air purification system, an active phytoremediation system, which you see here. And this allows for indoor air to be continuously cleaned, offering healthy indoor space within the interior, even if the outdoor air supply is polluted. And in New York City climate type, we calculated that this microfarming wall would provide daily fruit and vegetable nutrients needed for a family of 4 for 260 days a year. And in other climates, this could be even more. And I should say the design was designed to accommodate a family of 4. So there was the loft space you're seeing up here, had a bedroom, and then there was beds that kind of could easily be converted into a bed or a sofa space. So the design itself followed a modular approach. And here we see Amina Mohammed, the Deputy Secretary General, harvesting pepper from the wall. And the wall actually also enhanced biodiversity, with local honeybees finding their way to these flowering plants over the summer. And this is the team on the plaza. We actually erected the whole building in 3 days. So all of the building systems are modular design, so they were easily transported and erected on the project during that 3-day time frame. And the actual building itself was designed and fabricated offsite and then brought here, and through modular design and construction was easily put in place. And we included the SEVA framework I just talked about as part of this project, because we really wanted to monitor both the interior and the exterior environmental conditions of the site, as well as the functioning of the different systems. So what you're seeing here is where we actually placed sensors around the building, and this is what I've shown before. Through SEVA, we actually visualized the data, and were able to show on site. We had a screen as part of the house to show in real time the air quality, the solar electricity consumption and generation, as well as the temperature and the humidity. And we also use SEVA to track and showcase how the B framework and the ELM related to the UN SDGs. We use this to also as a kind of organizational tool throughout the project, to show how different variables, were allowing us to achieve the different UN SDGs, but also to use it as an organizational tool for the different members of the team. And this highlights that, the ELM and the B framework contributed to 8 of the 17 UN SDGs. So we outline how this built environment ecosystem framework can enable the association of SDGs as an integrated package, with the ELM performing as this scalable but self-reliant ecosystem of systems that can enable systemic change. And future research is towards scaling up in density of such housing systems across multiple climatic and cultural contexts, to really allow for ubiquitous sustainable urban housing. But again, as I said, to kind of use this regenerative design approach to apply it to local contexts. So that was one of the key things there. And I'll finish with just briefly talking about a current project on circular economy and housing, And this project, which is in the early stages, is called Data Homebase, a prototype visualizing Canada's housing characteristics to foster a circular economy. And this project is part of an interdisciplinary effort led by myself and Professor Avi Friedman and Professor Michael Gemtrud at the School of Architecture. And it's part of a CMHC challenge addressing Canada's housing supply. So the challenge was this: how can we create data solutions that improve decision-making for housing supply across Canada? And upmost on our mind were two key challenges that affect Canada's housing supply: affordability and sustainability. And there is an affordability challenge. On average, Canadians spend almost 46% of their gross annual income on housing, which is well above the 30% defined rate of affordable housing. And for the past 10 years, for example, in the past 10 years, Montreal home prices have increased by 43%. And in terms of sustainability, 20 to 30% of Canada's solid waste stream is construction, renovation, and demolition waste. And as governments work to achieve the Paris Agreement goals, there's a push to reduce greenhouse gas emissions associated with buildings, such as this Vancouver's zero emission building plan and Montreal's recent mandate for the disclosure of greenhouse gas emissions from buildings, which includes dwellings. So one approach that we wanted to look at was how a circular economy could help tackle the housing supply challenge. So our question became, how can circular economy and flexibility principles support the building of affordable and sustainable housing? But as I mentioned, this was a data-driven round. So we looked at data related to these issues and found that although data exists, it's currently scattered and making evidence-based decision-making all the more difficult. So to overcome this barrier, we've proposed to develop housing passports, which are standardized digital descriptions of residential building characteristics. So for our proposal is Data Homebase, which is a new web application visualizing the housing passport information, offering standardized and contextualized digital descriptions of housing. So structurally, Data Homebase consists of housing passports, which consists of building and material characteristics and attributes, allowing for their organization. And it provides users with a standardized analysis of circular policy and financial precedents, as well as a toolkit for the implementation of a circular approach. And in order to showcase what this standardization means, we've collected a number of case studies and mapped their data to this standardization framework. In other words, we've created housing passports for a number of different housing case studies. And as well as the case studies, we're also creating two innovative demonstration projects or archetypes of typical housing typologies with initially a focus on Montreal. And these are the multifamily and the single family circular housing. And we've integrated modular and flexibility principles in their design, such as modular construction and flexibility of bathroom, kitchen options, for instance. And then these archetypes are integrated into the toolkit feature of the Data Homebase application. And using this easily accessible data visualization, a user can make changes to the geometry, the materials and the components of the demonstration archetype. And in real time, they see how their choices affect the building's appearance and its occupancy type in terms of layout configuration, but also the environmental and economic costs associated with that decision in terms of embodied carbon, energy efficiency ratings, as well as cost for new versus recycled materials. And these results that you see as kind of a benchmarking here are based on extensive analyses where we use life cycle analyses to look at the embodied carbon rating and life cycle cost analysis to look at the cost comparisons. So we believe that the data that can be accessed through the web application can be very useful to different user groups, whether it's home building sector actors wanting to understand environmental benchmarking of housing in terms of operational energy and carbon emissions, whether it's financial stakeholders requiring data to complete affordability and green financing property assessment, or whether it's policymakers needing data for evidence-based policy generation or to show contributions to the UN SDGs targets and indicators, or to understand socioeconomic context of the different housing and the demographics of an area in terms of housing affordability. So we're confident that data home-based can be valuable to these three key stakeholder groups because we've taken a pragmatic approach to its design, and many of its features are influenced by conversations we've had with a variety of housing stakeholders during the proof of concept design process. And this engagement with relevant parties has allowed for this new feature, because one of the things that we learned from our conversations was that a circular economy approach to housing supply relies on communication across stakeholders in the housing value chain. And this, which you're seeing, is the implementation and building capacity aspect of data home-based, which allows a user to explore these different stakeholders in regions across Canada to really try and incentivize cross-industry collaboration. And these are just some of the groups we spoke with that highlighted the importance of the data home-based tool for affordable and sustainable supply decision-making. So we're excited to continue this research, and we believe it has significance in creating a platform that will allow for evidence-based decision-making in the housing sector towards affordable and sustainable housing practices, that it can help with easing transition towards a circular economy in Canada's housing supply, and potentially incentivize cross-industry collaboration for increased affordability and sustainability. And this work would not be possible without collaboration of this outstanding interdisciplinary team made up of members from industry, government, and academia, as well as the kind support of CMHC and the Housing Supply Challenge. So I'll leave it there, and I'm happy to take any questions, and thank you for listening today.
Thank you, Professor Keena. That was great talk, and it's really amazing how you've brought so many different factors into one package that should be sort of very useful by various stakeholders in the industry. So there are questions that are popping up on the screen. So I just, let me maybe take the first one over here from Joanne Whitmore at HSA Montreal. And so the question is, implementing circular economy strategies is often data intensive. How do you access all of the data needed to map out the material energy and greenhouse gas flows at regional levels, for example, provincial or city levels? Official data at these levels seem to be confidential or not available.
Okay, thank you. That's a great question. So I think you're right, and one of the challenges is always to find data that's specific and relevant, so that the results of, let's say, understanding the life cycle impact of a certain building is relevant to that building. So what we've done with looking at the different cases that we've worked on so far is that when running, for instance, I'll take the example of life cycle analysis, or trying to understand the embodied carbon or energy in a building, where we start by, and especially in the last case I just talked about, the housing supply in Canada, where we're trying to look at a large range of building stock. We started by looking for LCA inventory databases and data that's relevant to North America, and then specifically looking at environmental product declarations that manufacturers of construction materials and components within Canada or the US provide, right? And they typically look at that early stage of the life cycle. So they're looking at the life cycle impacts associated manufacturing and material extraction and manufacturing of that product or service. So by incorporating that data, it's closer to where that building is. So in that way, it can become more relevant when we run the analyses. And then there are other large data sets which are coming out of different places, like the Eco-Invent from Europe, which can be used as proxies for the development of certain materials if we can't access data that's specific to the region that we're looking at. So I hope that answers your question.
Great, thank you. In the interest of time, we'll jump to another few questions if you can. So the next question is from Eric Trottier, I believe from ETS. So his point is that the one platform to rule them all approach has failed time and time again in the construction industry. For example, ERPs in the 80s and 90s, and now CDEs. How does this proposed tool account for this and support interoperability with existing tools and processes in the asset industry?
Yeah, that's a really great point. And that was one of the things that we're very focused on in developing the SEVA tool. That I talked about the kind of ecosystem intelligence. We wanted that this tool could be used throughout the built environment process, so that different stakeholders could communicate through the tool, right? And you could track the life cycle of a building because through a virtual kind of life cycle, if you like. Through the interoperability, we're using, I didn't go into this in detail, but the back end is based on semantic web infrastructures, and we use web ontologies, which allow for that interoperability. So we imagine that the tool will be used by the different entities. So it's the user who's uploading the tool or uploading the data to the tool. But when they upload the data, they're uploading data and metadata that's linked to an ontology, which then allows for that interoperability because they're using ontologies that are machine readable and also understandable at the web level, if you like. So that's one of the ways, by creating this knowledge graph, that it's not a top-down process. It's trying to be more of an ecosystemic kind of approach, if you like. So allowing for people to be able to upload. I showed where different analyses were uploaded. So they would be uploaded from analyses coming from a BIM model, for instance, or embodied energy analysis or something like that. So being able to upload your tool and upload the analysis from the tool was important. So we're not saying that the analysis is done through SEVA. It's like once you have the data and once you have the different tools you want to use, they can be uploaded. So that was one of the key thought processes behind its development.
So I guess we'll move to the next question, which is from Professor Graham Clark at Bioresource Engineering at McGill. And his comment is that I agree that solutions for sustainability cannot be focused on tools only for industry and supply side actors, but also on consumer preferences. How do we address this?
Yeah, that's a great question. And you know, I think part of it is allowing for tools that kind of show the process more, so we understand what's happening more, so that the consumer can feel more agency. Whether that is, you know, allowing the consumer kind of have an app of the building they're working on, so that they can, you know, understand how it's performing, right, in terms of even just for occupancy comfort, you know, being able to understand which part of the building has warmer zones or which part is cooler zones or something, you know, that technology can help in that kind of way. And I think it's about kind of creating a certain level of kind of transparency around buildings too, so that understand their impacts and their performances. And in that way, we're kind of allowing a visibility that the consumer can understand and can maybe challenge how they want their building to function more. But I think it's a huge question, because consumers have such a role to play when we're talking about sustainability and buildings.
Thank you. So this question from Susan Reed, who would you recommend that we talk to, or would you have any suggestions for sustainable renovations for very old buildings, like 100-year plus, legacy buildings?
Yeah, that's a great question, and maybe I can follow up with Susan on some of them, because we're looking at different part of the research we're doing, and another project we're doing is looking at kind of mapping the construction, renovation, and demolition waste within the context of Montreal, and looking at, there's a lot of different suppliers and industry and organizations out there that work to actually reclaim these materials and reuse these materials. So there's a strong network of that, and so there could be a place where you could really look for good practices in thinking about repairing that roof. So, great.
So thanks very much, Professor Keena. I think it'd be wonderful to continue this conversation, but in the interest of time, we'll wrap up today, and just hope that this conversation will continue on the side. So thank you again very much, Professor Keena, for taking the time to share your work about the model, the SEVA model, and the whole background to it. So that was very, very informative. And with that, I would just also like to thank the TISED team for all their help in putting this seminar together and the arrangements. And I wish everybody a wonderful day, and look forward to seeing you at our next event, which will be posted soon. Thank you.
Thank you. Thanks so much.